We're back for our final video on section 6.2, properties of power series. Remember, what we're doing in this section is we're combining known power series that converge on some interval of convergence into new power series by adding them, subtracting them, multiplying by a constant, multiplying by x raised to a constant power, or by composing them, putting a function in place of x, a function that depends on x. We can also multiply them together. We found that some of these rules and some of these processes change or affect the interval of convergence, and some of them do not. Multiplication does not affect the interval of convergence, and neither does addition or subtraction, or multiplication by a constant, or by x raised to a constant power. However, the substitution of a function dependent on x in place of x could affect the interval of convergence, where that substituted factor has to fit within the original interval of convergence. Now we want to turn our attention to the final two ways of creating new power series from old ones. In this particular video, we want to take a look at integrating power series term by term, or differentiating power series term by term to get new power series. And of course, we can do the same thing to the functions they represent over the intervals of convergence in order to figure out what functions they now represent. Let's take a look at what we're doing. I'll share my screen with you so that you can see the subscripts more easily. In the screen that you now see in front of you, we're looking at either differentiating or integrating power series that are known to converge on some interval I. We're going to start with a power series C sub n x to the n that you see here, which can be written as C sub 0 plus C1x plus C2x squared plus C3x cubed, and so on. We know it has some interval of convergence, and we know, therefore, that we should be able to integrate and differentiate. And that's what we're going to do in this video. If we take the derivative with respect to x, which is our variable, not with respect to the index of summation, which is n, but we take the derivative with respect to x, because the derivative doesn't depend on n, the index, it can come inside. And again, because C sub n is a constant coefficient, which depends only possibly on the index of summation n and does not depend on x, we can in fact take the derivative inside of that and apply it to just the power series part, x to the n. Now, we know how to apply the derivative to x to the n. We apply the power rule for derivatives, which gives us nx to the n minus 1. Now, if we were to write this out in the terms c sub 0 plus c1x plus c sub 2x squared and so on, and we were to take the derivative term by term, this would give us, well, the derivative of a constant 0, so the first term drops out, and we get c sub 1 plus 2c sub 2x plus 3c sub 3x squared plus 4c sub 4x cubed, and so on. So there is a pattern developing. Now, this is what would happen if we were to differentiate it. What would happen if we were to integrate it? If we're to integrate it, again, we're taking the integral with respect to x, and the summation only depends on the index of summation n, not upon x. So we can pull the integral inside the summation, and since c sub n only depends possibly on n, it's some representation for the constant coefficients, then we can pull the c sub n out of the integral, which is dependent only on x. Now, the x sub n cannot come out, of course, because it depends on x, and that's what we're integrating with respect to. Now, we know how to integrate x to the n with respect to x. That's the power rule for integrals, which gives us x to the n plus 1 divided by the new power n plus 1. Now, if we were again to represent the original power series with its different terms, and we were to integrate term by term, we would get c sub 0 x plus c sub 1 x squared over 2 plus c sub 2 x cubed over 3, and so on, plus we would get a constant of integration because this is an indefinite integral. So what we're saying is that for power series that converge on an interval, we can differentiate and integrate them term by term. Let's now take a look at what happens to the interval of convergence. The basic interval of convergence doesn't change, but what happens at the endpoints may change. This is something new that we have not seen before. We have not seen this kind of change before. Before, nothing changed the interval of convergence except the substitution of a new expression dependent on x in place of x. Now what we're hearing is that while differentiating and integrating doesn't change the basic interval of convergence, it could change the convergence at the endpoints, totally new, something different, which means that we're going to have to recheck the endpoints of the original interval of convergence. It'll be basically the same, but we won't know what happens at the endpoint, so we'll have to test those separately. So this is a new rule for us. Let's take a look now at the theorem of term-by-term differentiation and integration of power series. We're going to suppose that we have some power series centered at A, where A could be 0, but it might be some non-zero constant. And we have the power series from 0 to infinity of c sub n x minus a to the n. Suppose that this power series converges on some interval of convergence from a minus r to a plus r for some value of r greater than 0. So again, it could possibly be the entire real number line. We're going to let the function f defined by the power series f of x right here be represented by the sum of these terms. And this is just writing out the terms of the power series. And this is true for the magnitude of all x minus a less than r. This is because it's written in basically geometric form. Now, we know that f is differentiable on the interval from a minus r to a plus r, and we can find f prime by differentiating the series term by term. So that means that we take the derivative on the inside as we did before, so n times c sub n x minus a to the n minus 1, which gives us this expression you see here in x minus a. Very similar to what we saw previously, but just with x. Now, this is also going to have the same interval of convergence, except we don't know what will happen at r and negative r. We'll have to test those endpoints separately. Now, we can also integrate term by term over the same interval of convergence, and we can find the indefinite integral of f of x dx by integrating term by term. But again, even though it doesn't change the basic interval of convergence, it could change what happens at the endpoints. And we see this in the rest of the theorem that you see here. So again, you do get the constant of integration coming out, and you get the basic integration term by term based on what we had previously. Now, the proof of this theorem it's way beyond the scope of this course. So we're not going to prove the theorem. I'm not even going to sketch it. It's not in the textbook. It is significantly beyond the level of calculus 2. So we're not going to cover it. You're just going to have to take it on faith. Now, this theorem does guarantee that you can integrate and differentiate and get a new power series. It also guarantees that the basic interval of convergence stays the same, but it does not say what happens at the endpoints. So you'll have to check the left endpoint and the right endpoint of the interval of convergence separately. You're going to have to check them again. We actually did some of these in the first section of this chapter, section 6.1, when we were talking about power series and functions. So we've already done some of this. So we're only going to work 2 examples here today. We're going to take a look first at example 9. In example 9, we want to differentiate the given series term by term to obtain the corresponding series expansion for the derivative of f. So we have both the function representation, 1 over 1 minus x squared, and the power series representation, which is the series from 0 to infinity of x squared to the n, or x to the 2n, if you want to write it that way. Again, writing it as x squared to the n follows that basic geometric form, and that's why we know that it converges to 1 over 1 minus x squared. We're using that basic rule. So what we want to do now is we want to go ahead and write down what the original convergence is going to be. So originally, so we'll look at the first one. It converges for, and this is one where we substituted x squared in place of x. And remember, over here to the side, we have the series that's equal to 1 over 1 minus x, which is the one from 0 to infinity of x to the n. So we replaced the x with x squared in both the function representation and the power series representation. And because this is a composition type thing, a substitution, then we know that it will converge provided what we substituted, which is x squared, meets the original conditions of convergence. And the original conditions of convergence for this one is the magnitude of x less than 1. So that means that ours is going to converge for the magnitude of x squared less than 1. Now, when we look at the magnitude of x squared, we can drop the absolute values because something squared is definitely non-negative. And that gives us x squared is less than 1. Now, when we take the square root of something squared, we don't get x. I know that a lot of students think that. It was bad pedagogy in some of your high school textbooks that said, always assume everything's positive. Well, that doesn't happen in the real world. When you take the square root of x squared, you get the absolute value of x. And when you take the square root of 1, you get 1. So we have that the magnitude of x is less than 1. So these actually have the same interval of convergence. Even though we substituted an expression dependent on x in place of x, it didn't change the interval of convergence. Sometimes it does, sometimes it doesn't. You have to check each one individually. So we know what the original interval of convergence is. So now what we want to do instead is we want to go ahead and write out what it would look like term by term and what it would look like in function form. So I'm going to go ahead and scroll up just a little bit, and we're going to write this now in term by term form and also in function form. So in the term by term form, I have the series from n equals 0 to infinity of x to the 2n. Now, what is that going to give me? Well, when n is 0, 2 times 0 is 0. So x to the 0, remember, we defined that no matter what the value of x is, we defined that to be 1. So this becomes 1 plus, and then when n is 1, we get 2. So I get x squared. And then I get x to the 4th. And basically, I'm getting all the even powers of x from that point on. Right? So this is what my series looks like term by term. Now I want to take the derivative of this thing. So I'm going to take the derivative out here. So I'm taking the derivative of this expression from n equals 0 to infinity of x to the 2n, which would be the derivative with respect to x of 1 plus x squared plus x to the 4th plus x to the 6th plus so on. And I know how to do it term by term. I know what that's going to give me. If I do it term by term, this in essence is just going to give me 0 plus 2x plus 4x cubed plus 6x to the 5th. And if I went one more term, we'll do one more, plus 8x to the 7th plus dot, 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 right? So it keeps going from there. So we've got the different terms written out for the derivative. Now, what would happen if I were to apply it in the formula form? What would I get? Again, the summation depends on n The derivative does not, so I can pull the derivative inside of the summation. And so I get the sum from n equals 0 to infinity of the derivative with respect to x of x to the 2n. Now I have to take the derivative of that. And when I take the derivative, I just apply the power rule. So I bring the power to the front and reduce the power by 1. So this is going to give me the sum from n equals 0 to infinity of 2n times x to the 2n minus 1, which is equal to this expression that you see up here, 0 plus 2x plus 4x cubed plus 6x to the 5th plus 8x to the 7th plus dot, dot, dot. Except we have a little bit of a problem. Does anybody see what this problem is that we have? What's happening to the first term? The first term ended up being 0, but I haven't taken that into account here. But in fact, that first term is a constant. So one thing I can do before I take the derivative is I can rewrite this one because I know that first term is a constant. It's going to disappear. I can take this and I can rewrite it instead in the following form. So this is going to be written as, and I'm going to take the derivative back outside, and this is going to be the sum from n equals 0 to infinity of x to the 2n, which becomes the derivative with respect to x of the first term, which is 1, plus the sum from n equal 1 to infinity of x to the 2n. Now, why do I need to do that? The first term doesn't depend on x, but the series from 1 to infinity does depend on x. Again, look at the way you wrote it out. The first term is a constant. When you take the derivative, it's going to zero out. So when we take the derivative in power series form, we have to be careful that we've rewritten it in such a way that the power series does have x in every term. Now we can pull the derivative into what we have. So this is going to give me the derivative with respect to x of 1, which we know goes to 0, plus, and now I can pull that derivative into this power series starting at 1, the derivative with respect to x of x to the 2n. And this then gives me the series from n equal 1 to infinity of 2n times x to the 2n minus 1. And that's what generates the series that you see up here. So this is going to generate 2x plus 4x cubed plus 6x to the 5th plus dot, dot, dot. So it's going to generate those numbers. Now, if you're not sure, check it and see. Make sure that this works. If you check it and something doesn't work, it's probably because you didn't pay attention to the fact that the first term didn't depend on x, and you didn't rewrite the power series with that term pulled out. In other words, the first term doesn't match the pattern of the rest. So what do? We chop off the head and set it aside. This looks like you get from one term to the next by multiplying by x squared, but that doesn't exactly work for the first one. So what we're going to do here is we're going to look at this and we're going to test it. So we're going to let n equal 1. So 2 times 1 will give me 2. 2 times 2 is 4, or wait, oh, it was 1. 2 times 1 is 2 minus 1 is the first power. So now I'm going to let n be 2. I'm going to keep my fingers up. 2 times 2 gives me 4, so that's the second coefficient. And then 2 times 2 is 4 minus 1, which gives me 3. Remember that 2n minus 1 is always going to generate an odd number. So once I have the first one, it's going to generate the odd numbers in succession after that. So first, third, fifth, and the seventh. And the coefficients are going to be the even numbers, starting with 2, 2, 4, 6, 8, and so on. So in fact, this pattern for the power series starting at 1 does generate the series that you see on the right. But again, we did have to pay attention to the fact that the first term didn't match the pattern of the rest, and we had to take that out because it didn't depend on x before we did the derivative in power series form. Now, when we look at this particular one, remember that this was giving us the function 1 over 1 minus x squared. So we're looking at the series 1 over 1 minus x squared. That's our function, and the series is from 0 to infinity, x to the 2n. So we've taken the derivative of it. So let's rewrite down here what f was. So f was equal to 1 over 1 minus x squared, but it was also equal to the power series from n equals 0, and I'm trying to make sure I copy this correctly, to infinity of x to the 2n. And again, you can separate the 2 and the n, and you can think of this as the series from n equals 0 to infinity of x squared to the n, which again tells us that we're substituting x squared in place of x in the original power series, the basic one. So this is our function, and we took the derivative of this. We wrote it out term by term. We noticed that we had to separate the first term from the rest, and we took the derivative in power series form, and we took the derivative term by term, but we haven't taken the derivative of the function yet. So let's go ahead and apply the derivative to f. So if I want to rewrite f in a better form for taking the derivative, I would rewrite it with a -1 exponent. So I would lift the entire expression in the denominator to the numerator with the -1 power. And once I do that, then I can compute the derivative doing the power rule. So this gives me -1, 1 minus x squared to the -2, which gives me a -1 over 1 minus x squared quantity squared. Okay, so this is the function that I have for the bottom. So what does this mean? Well, what this basically is telling me is that the original series, which was this one up here, which represented this function, I can differentiate it term by term, and I can get that f, oops, how did that become a -1? That's f prime. So f prime, which ends up being equal to -1 over 1 minus x squared quantity squared, can be represented by that power series. So let's scroll up again and see what that power series was. It's this one right here at the bottom in blue. So this gives me the power series from n equal 1 to infinity of 2n x to the 2n minus 1. Now, I can only use the power series to represent this function on the interval of convergence, which I need to check. So the original interval of convergence for this one, we based it off of here. Then we substituted x squared for x, which carried the same interval of convergence, which means the interval is between -1 and 1. But we have to recheck the endpoints. So if we're going to recheck the endpoints, we don't know what happens at -1 and 1. So we know it converges between open -1 and 1, but we don't know what happens at 1 and -1. So we have to test those separately. So when we test them separately, let's go ahead and write that down. So we're going to test left, which is going to be x equal -1. So we put it into our power series, n equal 1 to infinity, the quantity 2n times -1 to the 2n minus 1. Now, as you might expect, this is not going to converge. Why not? Well, the -1 to the 2n minus 1 is going to give us basically -1 to an odd. So they're going to, they're always going to be odd. So it's always negative, basically. And then we have 2n here, which means if we want to write out some of these terms to see what's happening, it's not going to 0. If the limit of the sequence doesn't go to 0 by the divergence test, it diverges. And this one will not. So let's write out some. So the first term would have a -1 times 2. So I'd get a -2. All right, that's when n is 1. This becomes 2. This becomes 1. And -1 to the 1 is a -1. So I get -2. Now I let n be 2. Let's deal with the power first. So 2 times 2 is 4. But 4 minus 1 is 3. So no matter what I do, this power is going to be odd. And -1 to an odd power is always negative. So this is going to give me, for the next term, when n is 2, I get -4. And then I'm going to let n be 3. I know this is going to be -1 to the 5th, but it's still going to be a -1. And then this is going to end up being 6. So this is going to give me -6. Can you see what's happening here? This sequence of terms is not going to 0. The limit of the sequence of terms is not going to 0. It's going to -infinity. So we can say it diverges by the divergence test. So definitely at the left endpoint, it does not converge. So far we know it's from open -1 to something happens at 1. So now we have to check 1. You can't just check one of them, you got to check them both. So now we're going to test the right endpoint, which is x equal to 1. And we have the series from n equal 1 to infinity of 2n times 1 to the 2n minus 1 power. But again, 2n minus 1 is always going to be odd, but this is 1 to a finite power. 1 to a finite power is always 1. Power's infinity, it's indeterminate. But 2n minus 1 for a given n is a finite number. It may be huge, but it's still finite. So this becomes a 1, which means that this just becomes the series from n equal 1 to infinity of 2n, which of course is going to give us 2 plus 4 plus 6 plus 8 plus ... And again, it diverges by the divergence test. The limit of the sequence of terms is going to infinity. So what is our conclusion then? The interval of convergence is going to be open -1 to open 1. That's the interval of convergence. So we've represented the new function that the derivative is representing, and then we have the power series representation for that derivative, and we have its interval of convergence, and of course the radius of the convergence, or radius of the interval of convergence would be 1, right? Radius of convergence would be 1, right? So I hope this one made sense to you. It's a little confusing, remembering that you have to retest the endpoints when you integrate or differentiate, but there's really no way around it. You have to know the conditions under which they converge and what they converge to. That's part of learning about series. So now what we want to do, looks like I gave myself more room there than I needed. What I want to do now is I want to take a look at example 10. So it looks like this one got moved down a little bit. So let's try moving it back up. So this is our last example in this section. And then we have one more theorem to go at the very end. In example 10, we want to integrate the given series by expanding it. And we're going to integrate term by term from 0 to x. Now, this is something we have not discussed yet, but you've had this in the fundamental theorem of calculus, which probably made no sense to you when you learned it in calculus 1, and so you promptly forgot it. But remember that if we write the integrand in terms of a dummy variable like t, and we take the differential and make it dt, and we integrate from 0 to x, that what we're actually getting when we do that, this represents the indefinite integral of f of x dx, right? So that's sort of the definition of the indefinite integral. So the antiderivative function of f of x with respect to x is given by this integral from 0 to x of f of t dt. Now, why do we have to do this? Well, because we don't want to deal with that constant of integration. So you're going to see how using this other definition lets us get around that constant of integration. So we want to get the corresponding series expansion for the indefinite integral of f. So what we're basically doing is we're starting with a function and we want to integrate it. Now, this is what it looks like in function form, but we need to represent it in power series form because we want to be able to do this with a power series. Why? What's the point of using a power series? Well, this is a rational function, and power series are basically infinite polynomials where every term has some constant coefficient and a power of x. They're very simple polynomials. So they're much easier to work with, easier to compute, easier to program. They're easier to work with. And so we're going to rewrite this rational function in terms of the power series, which represents an infinite polynomial. So first, we want to represent this in a different form. Now, let's remind ourselves of what the basic form looks like. So the basic form, again, is the series from 0 to infinity of x to the n, which represents 1 over 1 minus x. This is the basic one. Again, this is a geometric series where a first becomes 1, and the common ratio is x, which gives us a first over 1 minus r, where this comes from. Now, how can we make this match this pattern? Well, the first thing I need to pull the 2x to the front. So I pull the 2x to the front. I do have a 1 in the denominator. That's actually generally the hardest part to get. I have the 1, but I don't have minus something that depends on x. And I have to, because that's what this is. So I make the plus into a double negative, and I write it as 2x times the fraction 1 over 1 minus a negative x squared. Now, this part at the back matches the format of the basic power series. And so I can replace this part with the power series from 0 to infinity by replacing x with negative x squared. That's what was in parentheses in the denominator. Now, I did have it also multiplied by 2x, so I have to multiply this by 2x. Now, remember, what affects the interval of convergence? We know the interval of convergence for the basic one is going to be magnitude of x less than 1, which is basically negative 1 to 1. That's the condition under which a geometric series converges. Multiplying by a constant power of x or by a constant 2 does not change the interval of convergence. It would stay like this. However, we also substituted negative x squared in place of x. That can, but doesn't have to change the interval of convergence. So we need to check. Now, if we're going to check that, we would have the new condition, of course, that negative x squared, the magnitude, has to be less than 1. Now, we've done this one several times today. The negative, when I take the absolute value, disappears, and I get x squared is less than 1. And then when I take the square root of x squared, I get the magnitude of x, again, less than 1, since the square root of 1 is 1. So in effect, that didn't change the interval of convergence. So it looks like it's going to be the same. So here's what I have so far to represent this function here, 2x over 1 plus x squared. This is a power series representation for it. Now, when I have this power series representation, one of the things that I want to do is I want to try to pull the negative away from the rest of the power series part. So I'm going to pull the negative off of the x squared, but it is being raised to the nth power, so that gives me negative 1 to the n. Now that would give me x to the 2n power. Now, where did this x come? This x is the x we have on the outside. Now, it's allowed to come in because we know this is a convergent power series on its interval of convergence from -1 to 1. So we're allowed to bring those in. In fact, we could bring the 2 in if we want to. So we have -1 to the n. We brought the x on the outside in here. And then we have the remaining x to the 2n power. Well, we have the same base, and we're multiplying. So we add their powers, 2n plus 1, which gives us the 2n plus 1 power. So we have this new power series representation. And again, we could pull the 2n if we wanted to. Now, we're going to apply the fundamental theorem of calculus, and we're going to integrate from 0 to x to get the antiderivative of the original function f, right? So we're going to do this. We're going to apply the antiderivative to f of x dx, which of course is equal to the integral from 0 to x of f of t dt. This is from the fundamental theorem of calculus. So we know this is equal to this. So we apply this definite of sorts integral from 0 to x with respect to a dummy variable dt, which means we have to rewrite the summand in terms of t, not x. So our x to the 2n plus 1 becomes t to the 2n plus 1. Now the 2 is a constant. It can be brought out of the integral. And the -1 to the n is a constant. It can be brought out of the integral. And the integral depends only on t, because the differential is t, and the summation does not depend, it depends on n, so I can bring the integral on the inside. So I slide it all the way in until I reach the factor that depends on t, the differential dt. So when I have that, remember how to apply this part of the fundamental theorem of calculus. Basically, you go ahead and you find the antiderivative of this. So t to the 2n plus 1, add 1 and divide by the new power. So t to the 2n plus 2 divided by 2n plus 2. And we have to evaluate between 0 and x. When we put in the 0 to the 2n plus 2 is going to be 0. So that part drops out and disappears. That's why this gives you the indefinite integral of f of x dx, because in essence, you're only putting back in the variable x. And so we end up with the expression, the 2 is still outside. We still have -1 to the n on the inside. It can't come out of the summation because it depends on the index of summation. And now we have x to the 2n plus 2 over 2n plus 2. Now, I want to try to rewrite this in a different format. So I'm manipulating things again. So now we have some algebra work to do here. So when we look at this, I can rewrite the 2n plus 2 by factoring the 2 off. So that gives 2 times quantity n plus 1 in the power and in the denominator. Now, once I have that, I can separate the second power from the n plus 1 power, which gives me this -1 to the n times the quantity x squared to the n plus 1 divided by the factor n plus 1. Now, this is starting at n equals 0, and I've got all these plus 1s here, but I know if I manipulate the lower limit of summation, if I push this forward by 1, I could subtract 1 from all the places in the summand where n appears. So I push this forward by 1 to get n equal 1, and I back these up by 1, which gives me -1 to the n minus 1, x squared to the n over n, which is a simpler format. It looks simpler. Is the first one correct? Of course it's correct. It's absolutely correct. It's just this one is simpler, and anything that looks simpler is, in math sense, better because it's more logical, right? Easier to see what the pattern is. So then we can rewrite the power series starting at 1 and going to infinity of -1 to the n minus 1 x to the 2n divided by n. So this is our power series representation for the indefinite integral of f of x, which was 2x divided by 1 plus x squared. So we have the power series representation for the antiderivative. Now we want to figure out what function did we just find the power series for? Because it's not f, it's the antiderivative of f. So we take the function 2x over 1 plus x squared and we integrate both sides. Now, we can do a basic u substitution where u is the denominator, 1 plus x squared. So du is 2x dx. Use the notation, swing the dx around. And we have 2x dx. So this is essentially du over u, which we know is the natural log of the absolute value of u plus that constant of integration. So what we've got then is the natural log of u, which is 1 plus x squared plus a constant of integration. Now 1 plus x squared, no matter what x is strictly positive. So I can drop the absolute values and represent this as the natural log of 1 plus x squared plus some constant of integration. In other words, I just found a power series for a natural log function. Not a rational, well, it is a rational, but a natural log function. So it started rational and it ended up being a natural log function when I integrated it. So the original power series here, 2x over 1 plus x squared, written in power series form here, has an interval of convergence from -1 to 1, and then we integrated it term by term, and we found that we got the natural log of 1 plus x squared plus a constant of integration. So this natural log of 1 plus x squared plus the constant of integration is this power series from n equal 1 to infinity, -1 to the n minus 1, x to the 2n over n. Why is this better? Well, natural log is a transcendental function. It's very difficult to work with, and it's very difficult to program into a computer or a calculator. But this is pretty easy. So all I have to do then, if I want to get a representation for natural log, is I just shift the center to get it centered at the right spot, and I can find a power series representation for any natural log, especially in this case, the one natural log of 1 plus x squared. In fact, we'll see it, we can do it anywhere in the next section, 6.3 coming up. So by term integration, it should be the original ones, but we have to recheck those endpoints. Now, I think we already did check the endpoints up above, or did we? No, I think we did not. We did on the previous problem, and I got mixed up. So here is our power series representation. This is it right here for the antiderivative of f, so the integral of f of x dx, which gives us natural log of 1 plus x squared plus a constant. And now we need to check the endpoints, because remember, when you take the derivative or you integrate, it could mess up what happens at the endpoints. Doesn't have to, but it could. So we're going to check them again. So we take this representation and we replace x with the left endpoint -1. Now, -1 to the 2n, we can split the 2 and the n apart. So this gives us -1 squared to the n. But -1 squared is 1. And 1 to a finite power is 1. So this becomes -1 to the n minus 1 times 1 over n. Well, -1 to the n minus 1 is going to alternate the signs. This is not always going to give you an odd. It's not 2n minus 1 or 2n plus 1. It's just n minus 1. So it's going to go even odd, even odd, even odd, or so forth. And so we're going to get alternating signs on what looks like the harmonic series. And this, of course, is the alternating harmonic series. And you remember from the alternating series test that the alternating harmonic series converges. The harmonic series diverges, but the alternating harmonic series converges. So we have convergence at the left endpoint. So far we know it's at closed -1 to something at 1. So we check the right endpoint, but we can do a similar thing. 1 to a finite power is 1. And again, this gives us the alternating harmonic series. So it converges. So we find that in this case, when we integrated, it did change what happened at the endpoints of the interval of convergence. Instead of being open -1 to 1, as was the case for f, the antiderivative of f has an interval of convergence from closed -1 to closed 1. Now, think about what you've done here. You've taken a transcendental function, natural log of 1 plus x squared plus a constant of integration, as an infinite polynomial. You represented it as an infinite polynomial, which are easy to do stuff to, by this power series over the interval from -1 to 1. This should blow your mind. This is a pretty remarkable thing to do, to represent a natural log function with the infinite sum of polynomial terms. Polynomials, super easy to deal with. Now we have one more theorem to cover before we end this video, and that's the uniqueness of a power series. So we saw in section 5.5, or 5, yeah, I think it was 5.5, we were talking about the alternating series test. We saw that conditionally convergent series had this weird fact that if you rearrange the terms of the series, you could get it to converge to a different number. I know, it kind of blows the mind. This is true for conditionally convergent series, the ones where the absolute value of the series does not converge, but the series converges without the absolute values. Those are called conditionally convergent. So they had this weird fact. Absolutely convergent infinite series, however, did not have that problem. If it was absolutely convergent, meaning if you took the absolute value of it and it converged, then it also converged conditionally. And in that case, whatever it converged to was unique. Any rearrangement of the terms would give the same convergent value for the series. So we have to ask ourselves, does integrating or differentiating term by term, is that going to give us, is it possible that by doing it in a slightly different way, a different technique, that I could have gotten a different power series for f? I mean, again, we could take some of these alternating series, rearrange the terms, and get it to converge to a different number if it's conditionally convergent. So who's to say that couldn't happen here? But the answer to the question is no, that cannot happen. In fact, if you have two convergent power series right here, and they're equal to each other, in other words, they represent the same function, then they have to be the same power series. So rearranging things, doing a different technique does not give you a new power series. There's only one power series representation. All right, the power series representation for a particular function f is in fact unique. This ends the video over section 6.2 when we're talking about how to create new power series from old power series. In the next video, things get a lot easier. I'm sure you'll be happy to hear that. We're going to be looking at particular kinds of series called Mclaren series and Taylor series. They are power series, but they're power series of a particular type. And they will allow us to represent other transcendental functions as power series. Functions like sine x, tangent of x, natural log of x, and e to the x. So I hope you'll join me for the next section's video.